We are talking about tree structures, and we have talked a little bit about how do we construct a tree. We can construct them to look like a binary tree with 2 children or multiple children. We've also said that there are some ways in which we can develop trees that, in addition to having the tree structure, have other constraints on them as well. For example, the binary search tree, in which there is an additional constraint of having a relationship between the parent node and the children node. One other thing that we can do with trees is we can search them and we can walk around them and we can process the data that's held in them. And an important skill to be able to reason with and to be able to describe with respect to tree data structures is 3 different kinds of traversal. Traversal is a word we use to talk about moving through a data structure as if you're traversing through the treetops or traversing through a store or something. We're moving through the data structure, and we're going to do it in one of 3 particularly structured ways that reflect the underlying tree branching structure that's present in our data structure. Not surprisingly, these 3 different ways are recursive. So the first thing that we'll consider, the first way of going through our tree that we'll consider is called in-order traversal. It's called in-order traversal because it reflects moving through a binary search tree in order from lowest to highest. And in order to do this, for example, if we wanted to print out all the elements that are present within a binary search tree, any binary tree, but usually it's applied to a binary search tree most often. It'll work in any binary tree. What we do is we think about it in terms of pseudocode. We say, what we're going to do is we're going to process the left branch recursively, then we're going to process our current node, and then we're going to process our right branch. So as we go through an in-order traversal, we think left, center, right. So if what we want to do is we want to print out all the elements of a binary tree, we say recursively print out everything down the left branch, then print out the node I'm currently at, so the data that I currently hold in my current node, and then print out all the elements of the right node. That's in order because our current node is in between the left and right side. What that looks like when we write it out in code is like this print method here. In this print method, which takes the parent node or the root node that we want to start with, you can see that first we check for the base case of any recursive call. We need a base case, and that base case is if what we're passed in is null. And if what we're passed in is null, good, we're just going to return. If what we're passed in isn't null, then we're going to recursively print the left side. Maybe parent.left is null, but that's okay because that'll be accounted for when we call that method, just like we just accounted for at the line above. Once we're complete with the recursive call to the left side, we take care of printing out our data. And then finally, we print out the data to the right side. And so in these 4 lines of code, we have the base case, recursive call on the left, processing our data, and recursive call on the right. And that's all there is to an in-order traversal. It's powerful, though, because of the effect that it has on a well-formed data structure. This is the recursive function, so often in the parent class of the binary tree, what we'll have is we'll have a method called print, which is not recursive, but that kicks off the recursive process by passing in the first node, which is going to be the root node that we're keeping track of. So that's this bottom code here where we print root. Okay, if in-order traversal is one of 3 ways of processing a tree recursively, what are the other 2 ways? Well, those other 2 ways are called pre-order and post-order traversal. The difference is when you process the node you're currently at. So in pre-order traversal, you first process the node that you're currently at, and then you recursively process the left side, and then you recursively process the right side. Post-order, not surprisingly, means that you process the node that you're currently at last. First you process the left, then you process the right, and then you process yourself. So our 3 different ways of traversing through a tree are pre-order, process yourself first. In order, process yourself in the middle. Post-order, process yourself last. Depending on how you use these different kinds of expressions, you get different kinds of effects. For example, a post-order traversal of an expression tree, printing out all the elements in your expression tree, will output reverse Polish notation. An in-order traversal of a binary search tree will output all of the data in your binary search tree in sorted order. So it's a very clever way of managing moving through your tree recursively and the data that you're keeping there. When might you use these different methods? Well, in addition to printing things out, maybe what you might like to do is you might like to delete all of the data in a directory. Well, to do that, it makes sense to first remove all the data from your children before you remove yourself, just to make sure everything is cleaned up. So if you think about a file hierarchy, maybe you have a sample code directory and a directory for chapter 1 and chapter 2. Well, what you want to do is you want to process the left and the right, and then process yourself last. So first you process chapter 1. You process the children first. First you process section 4. Section 4 has no children, so then you process yourself last. Delete section 4. You return to chapter 1, no more children, delete chapter 1. You return to sample code, there's more children, so you go down chapter 2. More children, go down section 1. Delete section 1, return to chapter 2. Delete section 2, return to chapter 2. Delete worked example 1, return to chapter 2, delete how-to 1, return to chapter 2. No more children, delete chapter 2. Return to sample code, we've deleted 1 and 2, no more children, delete sample code. So doing a post-order traversal enables you to process all of your children first. On the other hand, if you're going to copy a directory tree, you need to copy it in pre-order traversal. Because first you need to have a place for all your children to be copied to. So the first thing that you do in a copy of a directory structure would be to copy the sample code directory or folder so that you have a place to put chapter 1 and chapter 2. Then you proceed down chapter 1 and you copy chapter 1 and add it to sample code. Then you proceed down to section 4 and you add it to the copy of chapter 1. And you continue down chapter 2, creating chapter 2 and then 1, 2, worked example, and how-to 1. So copying a directory structure would require pre-order traversal instead. Now, because pre and post order traversals are very clear about when you process yourself versus your children, you process yourself first in pre-order and yourself last in post-order. That's very clear. But in-order traversal is a little bit unclear when you have more than 2 children. Because do you process yourself after the first child, or after the first half of your children, or after all but one of your children? In-order traversal on a non-binary tree is not well defined. And so we usually say that you can only do an in-order traversal on a binary tree because the structure of having a left child and a right child makes it very clear about when you process yourself. After the left, but before the right. This enables us to add an elegant bit of architecture to our search algorithm. And this kind of architecture is called the visitor pattern. In the visitor pattern, what we do is we create a special class, a class that has a method called visit. This structure is a little bit like the compare to structure in that we're going to create an interface that enforces a class to have one particular method. In the comparable case, the method that we insisted that all of our implementers had was compare to. In the visitor interface case, the method that we're going to require all of the classes that inherit from us to have is called visit. And the reason why we're doing this is because we can very elegantly separate out the idea of traversing through a tree from the work that we do at each one of the nodes. We allow the traversal through our tree to be done independently of the data, and we ask the visitor class to be responsible for processing the data. And so we can change the way in which our traversal works so that in a pre-order traversal, we'll take in both the node that we're starting at and an instance of the class that's going to do the work. So recursively, we do the same thing with our pre-order traversal. We say, okay, first of all, we're going to check to make sure we're not null. If we're null, then we'll just return. In a pre-order case, you take care of yourself first. And take care of yourself means we're going to call the visit method on the current data that we have. And this traversal, this pre-order method, doesn't care what's happening. It's just given this tool called visitor. The V parameter is the tool that it's going to apply to the data at the appropriate time. When it's done applying the data, when it's done applying the visitor method to the data, it recursively calls each one of the children, passing down the visitor class and starting at each one of the child's root, child subtree root nodes. We launch it all with a pre-order call that you see down at the bottom. And so what this enables the implementation to do is it enables you as a user of a tree to write a class that processes the data in the way that you want, but to leverage pre-existing code in order to do the traversal itself. For example, let's say that we wanted to count all of the names in a tree of names, that have at most 5 letters. So what we'll do, first of all, is we'll create a binary search tree, and we'll assume that it contains data in it. And then what we'll do is we'll create a class that implements the visitor pattern. We'll call this short name counter. Implements the visitor pattern, and so that means that it has to have the visit method. It can have other things. For example, in this class, we're keeping track of an instance variable called count. Because every time our visit method gets applied to one of the nodes within our binary search tree, we're going to update the counter. And that class is going to be passed down the tree, and it's going to have the counter variable updated as it's passed down the tree. So we then create an instance of our short name counter, and we go ahead and we call an in-order traversal using our visitor pattern to go through our entire tree. When that in-order traversal is done, we can look within our class to see what the instance variable counter has been set to after going through all the different nodes of our tree. And the value that it will have is reflected in the method that was applied to our tree, the visit method there in short name counter. So when we're done doing our traversal, we have the count of all the elements that are greater than 5. A very elegant bit of code that separates out the traversal from the work that's done, because the work that's done is very specific to the application, but the traversal is very universal. There are some times when you might want to move through a tree searching for something and stop the search at a particular point. Those two kinds of searches, the typical two kinds of searches, are called depth-first search and breadth-first search. And they reflect the way in which you visit the nodes. Depth-first search is like doing a it's like doing a pre-order traversal. And we can stop this process by using using a stack in order to keep track of the nodes that remain to be visited. So our goal here is to traverse through our tree, but stop when we've met some goal. Maybe we've found data that we're looking for, or we've added up count to a certain amount. Whatever our visitor class needs to do, we can keep track of that as our goal. So depth-first search is going to use a stack to track all the nodes that it still needs to visit. So in pseudocode, the algorithm works like this. Our depth-first search starts by pushing the root node off the stack. Then, iteratively, as long as our stack is not empty, we will pop an element off the stack. We will evaluate the element that we popped off the stack, and then we're going to push all of the children onto the stack, starting with the last one. And in this way, as we push things onto the tree and pop them off, we end up executing a depth-first traversal of our tree. So let's take this example of a tree over here on the left. The way we do this algorithm is we look at A first. We push A onto the stack. The stack is not empty, and so we pop A off the stack and look at its children, B, F, and G. We process each one of those nodes, and then we put G, F, and B back on the stack. We take the first element off of the stack, which is B. That was the last one. The last one in is the first one out. So we take B off, we evaluate B, and then we add each one of its children to the stack. C, D, and E. Sorry, we do it in the opposite order. E, D, and C. Actually, that's not consistent, is it? In the top case, we did G, F. Oh, no, that's consistent. No, not consistent. We did G, F, B, and then E, D, C. Well, they should be in the same order. They should be going either left to right or right to left. So in any event, we push the children onto the stack. We pop C off the stack, process it, it has no children. We pop D off the stack, process it, it has no children. We pop E off the stack, process it, it has no children. Now we pop B off the stack. We've already processed B, so we don't need to pop it off the stack. We pop F off the stack. We pop F off the stack. It has no children, so we're done. We pop G off the stack, we process G, then we look at our children, H and I, and we add them to the stack. Now we take the first element off our stack, H, we process it. No other children. We take I off the stack, we process it, and now we're done, having traversed through the stack in depth first order. So you can see that the way in which we processed elements using the stack as our traversal guide was to look at A, B, C, depth first, then D, then E, then F, then G, H, and then G, I. So going down depth first. Alternatively, if we would prefer to go through in breadth first order, meaning going across row by row rather than going deep first, we can do the same algorithm, but instead of keeping track of our nodes in a stack, we can keep track of them in a queue. So we would start with our root node A, we would process A and then add its children to the queue, B, C, and D. Now we pull the first thing off our queue, which is B, and we add the children of B to the end of our queue, E, F, G. But the next thing we process is not E, the next thing we process is the front of our queue, C. Nothing to do there, we're done with it, we put it back. Now the next thing on our queue is D. Wow, so there's some children of D, so we put H and I at the back of the line, ready to process. We don't process it yet. Now we look at what the front of our queue is, it's E. So we process E, no children, process F, no children, process G, no children, process H, no children, process I, no children. So by using a queue to keep track of the nodes that we're visiting, we end up doing a breadth first search where we do the layer with A, and then B, C, D, and then E, F, G, H, I. A different way of processing through your tree. In both cases, we can cause this to be a search that stops when we're done if we ask the visitor method to return a Boolean, true or false, after it has been called about whether the search should continue or not. Fortunately, Java has some of these methods built into it. But let's look at how we would implement it if we were implementing one of these strategies. So a particular implementation of breadth first search might look like this. We have an interface for our visitor class that says that anything that implements our visitor class must have a visit method and it must return true or false. In the class that actually does the traversal, breadth first, it takes in the visitor, it checks to see whether root is null, and if it is, it just stops. But if it isn't, it goes ahead and it creates a queue to keep track of our nodes. And now we add our root node to our queue to kick us off. As long as there are more elements, we'll have a sentinel called more. So while there are more elements and our queue size is not empty, we're going to go ahead and pull the first thing off our queue, queue.remove. We're going to apply the visitor pattern to it. And as long as there are more elements, we're going to go through and we're going to add we'll set more equal to the result of the visitor call. And as long as that came back true, meaning the visitor pattern didn't tell us to stop our traversal, we'll go ahead and add more elements to our traversal queue, which is all the children of the node that we're currently at. All right, so within Java, we can use an iterator that's available to us. So now we're not talking about our implementation of these methods. We're talking about the built-in version that Java has. So for example, we know that there is a tree set built into Java. We can have a tree set T. We can ask for an iterator of that tree set and keep track of that as our iter variable. We can walk through our tree asking for the first and the second elements as the iterator does the process of doing our traversal for us. And if the breadth first iterator was implemented here, we would have a queue that gets established. We have our breadth first iterator that starts at our root, creates the queue, and one by one adds elements to our breadth first implementation, as you see here. Okay, thank you for your attention. Let's do a little bit of work with this.